Okay, so we have seen the Peano axioms now, and one consequence of these axioms is that they will now allow us to define sequences recursively. What do I mean by a sequence? A sequence is an ordered list of objects. Specifically here, we are talking about infinite sequences. That is a list which looks like this: A0, A1, A2, A3, etc. And the terms go on. Okay, so this is the first term, this is the second term, third term, fourth term. So there is an order to the terms of the sequence. Now, what do I mean when I say to define this sequence recursively? Okay, recursive. By that, what I mean is this. Of course, since what we now have is just the natural numbers, nothing else we have right now. So the terms of a sequence for the time being will only be some natural numbers. For example, you may have a sequence like this, which is nothing but the natural numbers themselves in the usual order in which they appear, right? Starting with 0 and then incrementing the numbers one by one. Or we can have a sequence like this. These are the even natural numbers. We have not come, although we know about evenness and oddness, that we know. So we can use that knowledge to just see some examples. For us, we don't yet know what even and odd means, but just for the sake of showing some examples, we can consider them. One more thing is that in a sequence, it's not necessary for the terms. These are called the terms of a sequence or elements of a sequence. Sometimes they are called elements also. So this is the first term, this is the second term, and so on. So the terms are not necessarily distinct. We can have a sequence in which two terms can be the same. Or in fact, all the terms can be the same. We can have this sequence, say, where all the terms are equal and they are equal to 1. So these are examples of sequences, or more specifically, infinite sequences. Finite sequences also exist, but in analysis, infinite sequences are more important. Now, our 5 axioms allow us to define sequences recursively. Okay, so I am coming to that. What do I mean by defining something recursively? It is this. So how I define the sequence is this. Suppose C is some natural number which I have arbitrarily chosen. It can be 0, it can be 1, or something else. And I define A0 to be C. Okay, so the first term of my sequence is C. By the way, when we write a colon like this, right, I haven't talked about this. When we are defining something, we use a colon before writing this equal sign, equality sign. The part which is towards the colon, that is the thing being defined, and the part which lies on the other side, that is the meaning of this thing. So A0 by definition means C. By definition is equal to C. The meaning of A0 is C. So when you see these dots, it means something is being defined. So for example, if I say I write something like this: x is equal to y. It means x is defined to be y. Y is something that is already known to us, and x is something that is we are defining. Okay. If it is not like that, if we have something like this, x is equal to y, then I have to understand that x and y are already given to me, and this equation is telling me something about their relationship, namely that they are equal. This, however, just tells me that x is nothing but y. X is defined to be equal to y. Okay, so that's just a small thing. So how I am defining the sequence? The first term of the sequence is taken to be some natural number c. The second term depends on the first term. Specifically in this way, a1 is defined to be equal to f naught a naught. Now here I should say something. This is a function. We have not come across functions. I mean, we know from our prior knowledge of calculus and our prior knowledge of high school mathematics, we know what a function is. We will treat functions more formally when the time comes, but for now, functions are just just how we know them, are just some devices for getting answers or getting outputs when we put some input into the function. So for example, and here by the way, this function is from the set of natural numbers into the set of natural numbers. In general, we have seen functions like this. F of x is equal to x squared plus 1. They are often given by some sort of formula. Okay, some sort of expression defining the functional value. So, for example, if I put x equal to 1, then the function value will be 1 square plus 1 is equal to 2. So that's what functions are. We generally know what functions are. So in this case, f naught is a function from the set of natural numbers into the set of natural numbers. So that means if I put a naught into f naught, then f naught of a naught, this value is again some other natural number. So, and that is defined to be equal to a1, the second term of the sequence. And the process goes like this. The third term of the sequence a2 is defined to be equal to f1 of a1. Its value depends on the previous value, and this is yet another function, f1, again a function from n to n. f1 may or may not be the same as f0. Okay, and it goes like this, and so on. In general, we will define an plus plus to be the functional value of an, where the function is fn, where again fn is some function from n into n. These functions are given, okay. Once the functions are given, you can see that to make sense of this definition, I need infinitely many functions. For each natural number n, I need a function fn. And I am again stressing the point that these functions may or may not be distinct. They may all be equal also, just like sequences, ordinary sequences. The functions, here we have a sequence of functions, f0, f1, f2, etc. So they may or may not be the same, or some of them may be same, some others may be different. So all sorts of possibilities are there. So when we define a sequence in this fashion, then we say that the definition is recursive, where first of all we choose some base value, and then using that value we define the next term. In turn, using that we define the next term, and it goes like just like that. But the question is, if we keep on doing this thing, shall we actually get all the values of the terms in this sequence? I mean, this is an infinite process, right? So what is the guarantee that I will end up defining all an for every n? For that, to answer that, I need a result, and that result is known as the principle of recursive definition. So this is a proposition proposition 2116 because if you remember in the previous part of this video we discussed remark 2115, there we ended the discussion, right? So this is proposition 2116. So suppose that for each natural number n, we have a function fn which has the set of natural numbers as its domain and 2 into n itself. Again, for each natural number n we have a function. So there is f0, there's f1, f2. What these functions are we don't know. They are just some functions. Okay. And let C be a natural number. C is also a natural number because we need a base value, right? Then we can assign a unique value to an. We can assign a unique value, or I should, not unique value, a unique natural number. I should be explicit. A unique natural number, because that's all we have right now. Unique natural number an for or to every natural number n such that a0 is equal to c and an plus a suffix, the successor of n, is equal to fnan for all natural numbers n. Okay, so this is the statement of the proposition. What it says, for every natural number n we are given a function, and also we are given a natural number c. which can be any natural number. It can be 0 or 1 or 2 or anything. Then we can, to each natural number n, we can assign some other natural number or some natural number a n, which I am denoting by a suffix n because this a n depends on n. Once n is given, you can give some a n, some value. So to each n, there is assigned a natural number a n, and that is unique. For a given n, there is only one a n, not two values of a n. For example, if n is 1, then I may take a n equal to 2, but at the same time, or in other words, a1 is 2. Okay, when n is 1, a n is 2, or saying these two things together, I can say a1 is equal to 2. But I will not at the same time have a1 equal to something else. So there the uniqueness is not there. So here we need uniqueness. To each n there we can assign a unique a n such that there is a condition. And in these conditions the functions come. A0 equals c and the value assigned to the successor of n is equal to fn an. Okay, fn, the functional value of the nth function, at what point? At the value assigned to n. And this happens for all natural numbers n. So the question that that was raised here, since this is an infinite process, what is the guarantee that I will end up defining all the values? That answer is this proposition. Now we have to prove it. Okay. And this proposition will allow us to define things like this. And these definitions are called recursive definitions. I forgot to write some things. Okay. Let me write them here. It's called these things should have been written in the beginning itself. The principle of recursive definitions. This is the name of the proposition. So when we refer to this result, it's not necessary to say proposition to 116. We can just say the principle of recursive definitions. One more thing I forgot to write is that this, let me write it here itself. By now you are very familiar with this word informal. Why is this proposition informal? It's because we have mentioned sets and functions which have not been introduced to us yet. Although we know, but since we are suspending prior knowledge of these things, so this is informal. It will become formal when we have gone through all the things about functions and sets. Now we come to the proof. So since the proposition is informal, the proof will also be informal, but nonetheless the proof is not wrong. Okay, being informal and being wrong, there is a very big difference between these two things. And the proof uses the Peano axioms. Okay. So what is it that we have to prove here? We have to prove that for each natural number n, there exists a unique value of an. That's what we have to prove. And what is the strategy of our proof? We are using induction. In other words, we are using axiom 2.5, the fifth Peano axiom. Using the fifth axiom and proving by induction are the same thing. Okay, so this is our This is how we are going to prove the thing. So we start the proof like this. We apply induction on n to prove that we can assign a unique natural number an to each natural number n such that a naught is C and the rest an for all natural numbers n. This is what we have to prove, and for this we are going to apply induction on n. Okay, so naturally first we will look at the case when n is equal to 0. Okay, now here we start the proof. A naught is C, right? A naught is C, and if we want A naught to be C, we will take A naught to be C, and none of the other definitions means what? These an plus plus equal to fn an redefines a naught because of axiom 2.3. Now what have I said here? A naught, I want A naught to be equal to C. So I have taken A naught to be equal to C. So A naught is C, and none of the other definitions, these definitions, redefines A naught because of axiom 2.3. Why? What is the meaning of this statement? See, when we go on defining more and more terms, like A naught has been defined to be C, then we come to A1, which is nothing but A0 plus plus, and we define that to be this, and then we go to define A2 and so on. In this process, the value C of A naught does not change. Why? Because A naught appears here only. A naught is not equal to I should not say like that. This 0 that is appearing as a suffix here will not appear anywhere else on the left hand sides of these equations defining the terms of the sequence. Why? Because axiom 3 to third Peano axiom prevents us from having 0 as the successor of any natural number. So because 0 does not appear more than once, so A naught, its value continues to be only C, and there is no problem actually. We have A naught equal to C, and A naught does not appear anywhere else on the left hand sides. So A naught is C, and that is fixed. So that means for the value n equal to 0, I have a unique value of a naught, and that is c only, nothing else. If you recall, in one of the examples where we encountered a problem with a number system, there we had something like this: 3 plus plus is equal to 0. In example, okay, if I be specific, let me just see in what example we had this. Example 215. In example 215, 3 plus plus is actually equal to 0. If you go back to that example, you will see this. So, if on this number system that we had in this example, if I try to apply my induction procedure to try to define a sequence like this, then my a naught will be c, that is fine. Okay, and then I go to define a1 I have defined, a2 I have defined, a3 I have defined. Then when I try to define a4, which is a3 plus plus, according to my definition, it will be f3 a3. But at the same time, a3 plus plus is a naught also, because of the peculiarity of this number system. So a naught has two possible values, c and f3 a3. So a naught has been redefined. Now this clearly can cause problem if f3 a3 and c turn out to be not equal. Then I have lost uniqueness in the very first term itself. So that's why I need axiom 2.3. Axiom 2.3 has saved me from this sort of things. Okay. So my a naught value is unique. Now, and don't forget what we are doing. We are trying to apply induction. So that means we have to eventually be able to use axiom 2.5. For that, first I check the base case, then I assume that the result is true for some n, then prove it for the successor of n. So now, assume that we have assigned a, I have to write this up. Assume that we have assigned a unique value to unique value an to n. Okay, I have written value here, but you understand this is a natural number, right? Or should I write natural number so that when you look at these things later in future, there is no confusion. A unique natural number an to n, where n is some natural number. So this is my induction hypothesis. I have assumed that the result is true for n. Now I have to prove it for n plus plus. Now, an plus plus is equal to fn an So that means to the successor of n, to n plus plus, I have assigned a natural number a n plus plus. And what is that natural number? That is the functional value of the function fn at the natural number a n, because I have already assigned a unique value a n to n. So my a n is unique. So fn gives me only one value at a n, and that value is this one. No other definition. But here also we have to make sure that this a n plus plus is unique, and that is being assigned to n plus plus. No other definition a m plus plus equal to f m a m redefines a n plus plus because of axiom 2.4. A similar thing has happened here. What has happened here? Let us see. If you recall, in one example we had something like this, I think. 6 is equal to 2, so that means 5 is equal to 1. In one number system we encountered, we had 5 is equal to 1. From 4 equal to 0, if you remember, we can have 5 equal to 1. In that number system we had this, which is actually, we can write it like this also. 4 plus plus is equal to 1, or is equal to 0 plus plus. That is because 4 was equal to 0 in that number system. So if I try to define a4 plus plus, my usual definition of the sequence will tell me this is nothing but f4 a4. Okay. Now, but what about f4 a4? This is one value, some natural number, but at the same time a4 plus plus is also equal to a1, and these two values can possibly be different. That all of that depend on what these functions are, fn, and what the initial value is, c. Okay, there is no guarantee that they will always be the same. In fact, we can choose the functions fn carefully so that we don't need to be so careful. You just arbitrarily take some functions fn. Say f naught, you can take f naught of x equal to x, f2 of f1 of x equal to x square, f2 of x equal to x cube. Things like that we can take, and we will see that most certainly in any general case these two values will be different. It's highly unlikely that they will be equal. So there we will lose uniqueness of a4 plus plus, or a5 will have two possible values. So in that type of number system, if we try to run this process, run this proof, we cannot go forward. We lose uniqueness. And axiom 2.4 saves us from that, because if you recall what axiom 2.4 said, distinct natural numbers had distinct successors. So that means if n and m are different, then n plus plus and m plus plus are also different. So n plus plus, which I am now defining, this n plus plus value has not appeared before. Okay. Here you see a4 has appeared before, because a4 is equal to a0. Or For example, f5 has appeared before because f5 is equal to a1 because 5 is equal to 1 in that system, in that peculiar system. So that's why we have the problem here. But here axiom 2.4 saves us from that. Okay, so you see that we have used axiom 2.3, we have used axiom 2.4. What about axiom 2.1 and 2.2? They have already been used because to speak of 0, we need axiom 2.1, that there is a natural number called 0. And for every natural number n, it has a successor n plus plus. So axiom 2.2 has also been used here. Now we have only one more axiom to use, but that we will use as the last, in the last sentence, which is the axiom of induction itself, and that's what we are using. We are proving the thing by induction means we are using axiom 2.5. So you can see that to prove this, we actually need all the axioms. By the way, the proof is not over yet. We have to formally write it. Okay, because of axiom 2.4. So what have I achieved here? I have proved that A0 is unique. Then assuming the uniqueness of An, I have proved that An plus plus is unique. So hence,